Ever wondered if a computer could see the world like a farmer? Well, today we're going to find out. We are building an AI model, completely from scratch, to solve a real-world problem: how to analyze a pasture just by looking at a single photo. So let's dive right in.
It all starts with a pretty simple question. You look at a field like this, and you see grass. But to a farmer or an ecologist, this is so much more. It's biomass, and it's a super critical measure of how healthy and productive that whole ecosystem is. But how do you actually measure that? You can't just harvest the whole field, right?
Well, it turns out the answer is hiding in the pixels. We're going to build a model that can look at one picture of a pasture and figure out the amount of living stuff in it. This is where data science really gets its hands dirty, literally.
Okay, so here's our game plan. We'll start by figuring out the problem. Then we'll get our model the right data to eat. After that, we'll build its brain, teach it what's important, check its homework, and finally, we'll see if it can make a real prediction.
First up, the AI pasture problem. This is all about taking that real-world challenge and translating it into a language that a computer can actually understand.
So our goal here isn't just one number. Nope, it's a whole detailed breakdown. For every single picture, our model has to predict 5 specific things: how much green grass there is, how much dead stuff, how much clover, and then the total green matter and the total overall biomass. In the code, these are simply our target columns.
All right, let's move on to section 2, preparing the digital diet. And this part is absolutely critical because you've heard it a million times. An AI is only as good as the data it learns from.
We're going to follow 4 key steps. First, we load the raw data. Next, we reshape it to get it nice and organized. Then, and this is clever, we split it up. We make one set for the AI to study from and a completely separate one for its final exam. And lastly, we scale all the numbers, which just makes them easier for the AI to process.
Now, check out this transformation. The raw data starts out as this long, kind of messy list where every single measurement gets its own row. But then, by using a function called pivot table, we clean it all up. Now, each row is one single image, with all 5 of its measurements laid out right there in their own columns. This clean, organized structure is exactly what our model needs.
All right, on to section 3, building the vision brain. The data is all prepped and ready to go, so now it's time for the fun part: constructing the mind of our machine. It's called a Convolutional Neural Network, or CNN for short.
Now, the most basic building block of this brain is the convolutional layer. The easiest way to think about it is like the model's eye. It's this smart little filter that just scans across the image, and it's looking for basic patterns. The curve of a leaf, the texture of some dry grass, the sharp edge between light and shadow.
And here's the full blueprint. First, a bunch of those convolutional layers scan the image to find all the basic features. Then, things like ReLU and pooling layers process all that info, basically deciding what's important and summarizing it to see the big picture. And finally, a linear layer takes all that analysis and turns it into our 5 target numbers.
Which brings us to section 4, teaching with weighted goals. Because, building the brain is one thing, but teaching it is a whole other story. How we train the model is what really decides what it's going to learn.
I just love this analogy. In our code, the loss function is like the teacher, constantly grading the model's answers. And the optimizer, well, that's the study strategy. It's what the model uses to learn from its mistakes and get better each time. Together, they're what guides the whole learning process. But here's the secret sauce. We've decided that not all of the answers are equally important, and we can actually tell the model what to focus on by using these specific numbers. We call them target weights.
And this is exactly why those weights matter so much. See, without them, the model would just treat all 5 measurements the same. But with them, we're basically telling it, hey, that total dry biomass number, that one's the most important. By giving it a weight of 0.5, we're making its accuracy 5 times more important than, say, the Clover measurement. It really focuses the AI's learning on what we care about the most.
So after all that specialized teaching, let's head to section 5 and grade the learning curve. We put the model through 50 rounds of training, or epics as they're called, and now it's time to check its report card.
This is always the moment of truth, isn't it? Did all of that prep and building and careful training actually result in a smarter model?
And the answer is yes, it worked. Take a look. The loss curve on the left is like a golf score. You want it to go down, and it is. The model is making fewer errors over time. And the R-squared curve on the right, that's like a test score. You want it to go up. And look, it's trending up too, meaning its predictions are getting more and more accurate.
This is exactly what you want to see.
And that brings us to our final section, from pixels to prediction. This is the payoff. It's time to put our trained model to the test with brand new data that it has never seen before.
So during those 50 training rounds, we were smart about it. We saved the version of the model that did the absolute best on its practice tests. Now we load up that star pupil, the bestmodel.pth file, and we unleash it on some completely new images.
And here it is, the final result. For this sample image, the model predicts about 17.5 grams of dry green matter, almost 19 grams of dead matter, and a total dry biomass of 38.5 grams. All of that, just from looking at a picture. We actually did it. We went from a simple photo all the way to a detailed agricultural analysis.
So that's the whole journey, from pixels to pasture. It really makes you think, doesn't it? I mean, if we can teach a piece of code to see and analyze the health of a field, what else can we teach it to see? What's the next complex visual problem it could solve?